Hi everyone, I'm Anmol Dwivedi and I am a PhD candidate at Rensselaer Polytechnic Institute working under the guidance of Professor Ali Tajer. In this presentation, I'll talk about our work on linear discriminant analysis under f-divergence measures. Consider the problem of linear discriminant analysis or LDA. We consider two groups of data that are color coded as blue and red as shown in the figures on your left and right. We are interested in maximizing the separability between the two groups. From the figures, it is clear that the figure on your right finds a direction that is better separated in comparison to the direction found in the figure on your left. More formally, the following figure describes a block diagram to perform LDA between two groups of data. The n-dimensional random vector x denotes the feature vector that is generated according to probability measure p or q. Next, the random vector x undergoes a linear dimensionality reduction parameterized by matrix A, rendering the r-dimensional random vector y. Subsequently, a discriminator is used to classify the two groups of data in the lower dimensional space. In cases when the dimension of the feature vector x, that is n in our notation, is large, performing inference requires the computation of high dimensional statistics. For example, consider the likelihood ratio test to perform classification. In such a scenario, performing such a test becomes computationally complex for large feature vector dimension n, which as a result leads to the statistical computational gap between information theoretically viable tests that assume unbounded complexity and tests that can be performed under bounded computation power. The classical formulation for LDA optimizes the following heuristic objective function shown on your left, which involves the computation of between and within class scatter matrices. As a result, this limits LDA to classification problems to determine the underlying model of the data. Shown on your right is our formulation of LDA, where we select f-divergence measures as a measure of separation between distributions. This has three main features. First, it enables designing linear mappings for a wider range of inference problems. Second, it provides the designs that are optimal for the inference problem at hand. And finally, it enables characterizing the information theoretic performance limits, since information measures represent the true performance limits for various inference problems. To show the benefit of the proposed formulation and analysis, we next discuss numerical evaluations for specific choices of the divergence measure, which is the KL divergence measure. We considered the quickest change point detection problem, where the goal is to minimize the average delay. We run the optimal test algorithm under the following two designs of A. In the max LDA, we design A by always projecting the data onto the maximum modes of sigma. And in KLLDA, which is the KL divergence LDA, we design A by projecting the data onto the modes of sigma given by the theorems which are discussed earlier. We randomly generate sigma such that the eigenvalues of sigma are on either side of 1, and we calculate the average detection delay for various initial dimensions n and multiple reduced dimensions r. As shown in the figure, KL divergence LDA outperforms max LDA, resulting in a smaller detection delay.